Okay, well, hi, my name is Linas Vepstas. Linas Vepstas properly. You can call me Linus. I'm here to talk about automated, unsupervised learning of explainable, comprehensible patterns in language. And do that in a general setting that includes audio, video, or anything, the noosphere in general. I'm going to start by making some outrageous claims. I'm going to claim that the system, I'm going to present an algorithm here. The algorithm being presented here is capable of solving the famous frame problem, the symbol grounding problem as well. That one can learn common sense reasoning in this way. These are outrageous because these are, the basic claims of the holy grail of AI, of AGI. The algorithm I'll present is not particularly complicated. It, in fact, consists of some fairly well-known parts that many others have fooled with over the decades. It's not exactly uncharted territory. In this sense, most of what I'm going to say today is stuff that has been said before. Most of it may seem quite obvious, even simplistic or even naive. I will have to ask for your attention anyway, because you may find the particular combination to be surprising or unusual. Bear with me, I will start out simple. Okay, so everything in the universe is a graph. Not just the physical universe of stars and planets, but also, the universe of thoughts, concepts. Sparse graphs are necessarily labeled. This is because otherwise there is no way of talking about the things in that graph. The edges of a sparse graph are labeled by the vertexes at their endpoints. Graphs are decomposable. This should be obvious, but it's rarely mentioned in graph theory. You can cut an edge into two half edges. After cutting the edge, you only need to label the cut ends so that you know how to join them again. There's a metaphor I will use repeatedly. This is the jigsaw puzzle piece connector metaphor. Jigsaw puzzle pieces are designed so that the mating of these pieces is forced. When you cut an edge, you attach a connector to it. In this particular example, the polarity is indeterminate. You can flip a coin for which connector is which, but you might have to have the connectors there. While I'm on the topic, I should mention that connectors can be multipolar, right? They can be effectively multisexual. This is politically controversial, but biologists have found fungi with 43 different types of sex. Some of these different types can mate and produce viable offspring, and some cannot, right? So biology can be quite strange. In this diagram, in this chart, I've drawn a picture of a telescope jigsaw puzzle piece with connectors looking at the sun and the moon. Now, there are other things that can see the sun and the moon. The eyes, lenses, they have the same jigsaw shape. These shapes define the syntax of a graph. The syntax is exactly the collection of shapes that allow connections to occur. This is a definition of syntax. This might not be the definition of a syntax that you are comfortable with. May not be one that you've heard before. It is, however, entirely equivalent to conventional definitions of syntax. It's not even a particularly deep claim. It's fairly well known, fairly well understood. I'm sorry only in not having a good reference for it at my fingertips. Graphs are compositional. I mean, this is in fact so basic, such an obvious fact that we were like fish in water. We're not even aware of the water that we swim in. Right? And so I'll have to say some of these things out loud. Right? At the top of this chart, I drew a picture of a conventional definition of a term algebra. Right? Term algebra consists of a set of function symbols that take arguments. Arguments can be constants, variables, other terms. When you plug one into another, it has a name. It's called beta reduction. Terms are always directed acyclic graphs, DAGs, necessarily. People in symbolic AI, proof theory, programming and compilers and chip design, they all work with term algebras all the time. It's the stock of trade. If you're a programmer, you know this stuff. The only point that I want to make in this slide really is that jigsaw connectors generalize the concept of term algebras. One can assemble things that aren't just DAGs, but can be any directed, undirected graph in general. Some caution about these connectors. The connectors are, in fact, type theoretical types. Types have a structure. Types can have a very complex structure. And so basically the jigsaw diagram here is possibly a little bit misleading. The connectors are not necessarily so simple. All right? Type theory here is the same type that you're acquainted with from computer science. Right? Type can be an integer, a float, a string. Right? These are the primitive types. There can be compound types. There can be a list, an object-oriented class, a function signature. So all of these fairly complicated things can be types, and I'm oversimplifying a little bit by drawing a jigsaw puzzle connector to represent that. And as I said, I started out simple. Here's the first sort of point of confusion where things may start. Now I want to point out these things occur absolutely everywhere, and I'm just going to flash through some very quick examples. Right? Anything tensorial is going to look like a jigsaw connector piece. Here's one picture of a cobordism from a famous paper called The Rosetta Stone by John Baez. It explicitly talks about jigsaw puzzle pieces throughout the paper. The other little slide down here comes from a Bob Koch paper, Quantum Algorithms for Compositional Natural Language Learning. Again, the metaphor he uses in that paper is that we're assembling jigsaw puzzle pieces. By the way, that paper is kind of interesting because it presents a quantum algorithm that can perform natural language parsing in linear time. And so that's a rather unusual result. It shows up in, I wanted to just add, in the previous slide, anything tensorial is going to follow this sort of general idea. In biology, you'll see this in chemical reactions, right? Any sort of reaction has inputs, has outputs. You can think of those inputs and outputs as typed connectors. The reaction can't occur without those particular inputs and outputs. Another slide I want to bring to topic I want to bring to your attention is work by Prusinkiewicz, who's been doing algorithmic botany for the last 3 decades. He has actually some very stunning and beautiful work there, and I believe it is relevant to AGI precisely because it combines syntactic and semantic elements in the context, in a generic context, in a biological, botanical context in this case. I'm going too fast. All these ideas, they come from link grammar, right? This is where I developed my fetish for jigsaw connectors. The top of this chart shows a figure that comes from the original 1991 link grammar paper. That paper explicitly talks about jigsaw puzzle piece connectors. Underneath that, I drew an example parse from the link grammar parser. Kevin threw the ball. The S link there is the subject verb link. The O link is the object verb. There's a D connecting the determiner. English demands that there must be a determiner present. The diagram here, the diagram that I drew here is correct for this sentence, but I have to warn a little bit that the connector type system in link grammar is actually a little bit more complex than this. It's, the type matching is somewhat sophisticated. Types don't have to be primitive types as here, they can be compound types. Link grammar, just in case you haven't heard of it, I mean, it's on some side remarks here, right? It can be converted into head phrase structure grammar. It can be converted into a dependency grammar, into a categorical grammar, functional grammar. This can be done algorithmically. There's eye-watering mathematical proofs that can be found online showing exactly how to do this. I don't know how to control my mouse. If you haven't heard of link grammar before, now you have. It's real. I want to emphasize they're complete dictionaries for English and Russian. They're demo dictionaries for 10 more languages. Linguistically speaking, it's a legit linguistic theory. There are hundreds of published papers on the topic. You know, it's a real way of getting to syntactic and semantic structure in language. Now comes some of the interesting parts that I want to move with. Vision. Okay, this idea of shapes having of things having a jigsaw puzzle piece connector applies to shapes as well. I've drawn a stoplight. I've drawn an abstract graph corresponding to that stoplight. There are connectors. Some of the connectors are north-south. Some of the connectors connect to colors. Some of the connectors connect to the round shapes. Some connectors connect to a background, right? The point here is that the connectors are not just simple neighboring pixel connectors. This is not a pixel diagram. These are, some of the connections can be actually quite abstract. You can do the same thing for audio. Right? I have a fast Fourier transform diagram of a fast Fourier spectrum of a whale song that has been recorded. If you look very carefully on the bottom left of this image, you can see a sequence of 7 regularly spaced low frequency chirps. And I've tried to draw a diagram for that. Right? The chirp is a rising or a low falling sound, a wheat or wheat. In this case, it's a falling sound. The diagram just says, how would I recognize a chirp? Well, it's a fairly low frequency, so I have to pass each one through a low pass filter. They are separated from one another, so there's a finite impulse response filter that separates each chirp from the next one. There seems to be about a 2-second spacing between them. This is how one can recognize structure in audio. And now comes the key point, right? Where did these filters come from, right? How do you know to look for chirps? Surely it's not because some grad student has hand-coded up a bunch of filters just so, right? That's not the point of AGI. The point of AGI is you want to discover these filters from nothing at all, from scratch. Okay? So how do you do that? How do you find structure from nothing at all? And this is where we get into the hard part, the meat of this presentation. There's going to be some fairly dense mathematical talk here. I'm going to fly through this fairly quickly. There are many ideas that are well known. The ideas I'll present here are fairly well known in the machine learning industry. So if you're familiar with this stuff, it may not seem, the speed shouldn't be too great. A quick overview, I'll show how to build up a graph structure from pairwise correlations. And then I'll show how to generalize the particulars of that specific graph. That generalization turns out to be isomorphic to clustering. It turns out to be isomorphic to matrix factorization. So you can use either clustering algorithms or matrix factorization algorithms to do this generalization step. You might even be able to use neural nets for it. Seriously, I believe you can. No one has done it, but I believe it's quite possible. There's going to be a lot of neural net fans at this conference, so I can't steal their thunder. Okay. First concept that is key here is that of lexical attraction. We're going to start with a frequentist approach to probability. One observes things, counts how often they occur. Observing pairs is the easiest. One can blast through a large corpus of English text, say 1 million sentences, count how often you see word pairs, words close to one another, right, within 5, 6, a distance of 5 or 6 between each other. The fancy name for it is they're called 2 grams. Right. This gives you a count. I've drawn it on this slide as NUW for the the count of the word on the left and a count of the word of the right, how often that pair of the word left and right occur. Divide by the total number of pairs and you get a probability. The star here is a wild card, means sum over all possible values in that location. Right. Now, divide the pair probability by the marginal probability of the left word, divide by the marginal probability of the right word, take the logarithm, you get basic textbook mutual information. I'm calling it lexical attraction here because that's what Urich called it in his original thesis where he comes up with this. I need to distinguish it from another mutual information that will appear in the upcoming slides. But otherwise, it's the same concept. It's the same definition. The diagram at the bottom comes from Urich's thesis. And what he does here is actually, it's very clever. He draws a maximum spanning tree. The maximum spanning tree, it connects, right? There's an edge that connects every word in the sentence. The edges are chosen so that the grand total mutual information is the largest possible of all graphs. If you look at this, you can see that it presents a reasonable, in fact, arguably very correct parse for this English language sentence. Some things to note in the diagram. The mutual information for Northern Ireland is huge, right? Value of 11 here. This is because you don't see the words Northern and Ireland all that often in other contexts. I mean, of course, you do see the word Northern, you do see the word Ireland, but you don't see other words plus Ireland. They go together. This is what the mutual information is doing. It's saying these two words frequently co-occur. Now, given a maximum spanning parse, you can extract a grammar from it. Let's see, how is this done? This is done with, I already hinted at how to do this, right? You cut the edges. You draw the tree, you cut the edges, you label the connectors with the words that they used to connect to. On this page, I give you sort of several different ways of describing that piece, that connector piece. One of the way is to, all right, here's a text, first line is a text version. The minus sign here just says connect to the left. If I wanted those arrows pointing to the right, I would use a plus sign there. The ampersand simply says that both of those connectors must be present. That ampersand turns out to be a conjunction from a fragment of linear logic. It's not just a simple Boolean and, it's actually something a bit more subtle. Next line shows a tensorial notation. Tensors are very popular among physicists and those with formal mathematics background. It's popular in quantum influence thinking. Basically it's a very comfortable notation for people who do know tensors. All these notations are the same, and then the message here is that jigsaw connectors are tensorial. Those tensor indexes are the jigsaw puzzle piece connectors. And for the neural net, people notice that this whole thing looks like a skipgram. Right? It's a lot like it. It's a little bit different, but there's a, that correspondence is sort of a key bridge between these different languages. Now, I also wrote this as a word connector sequence pair, a WD pair. Now I use the word D for disjunct. D for disjunct, essentially because these connector sequences are disjoined from one another. You have a menu choice, right? You can throw a ball, you can catch a ball, you can see a ball, but if you're going to construct an English language sentence, you can either throw it or catch it or see it. You have a menu. You can't do all three things at the same, can't use all three words in one sentence at the same time. All right. So this is a disjunction. So this is a word disjunct pair is what we'll see. And now I can run the frequentist approach again. Right? You run through the corpus, you have a million sentences, and you count how often you see a given word disjunct pair. You get a count, and WD. You can turn that into a probability by dividing by the total number of observations. Given that, right? Given any specific word, now you can write down a vector for that word. The result looks just like a vector. I've drawn it at the, I've written it here at the bottom here. There's something a bit clever here, though. The plus sign here can be interpreted in two different ways. It can be interpreted both literally as a numerical sum, mathematical addition. It's also a disjunction, right? That plus sign indicates that you have a menu choice to be made there. So this is another part of another fragment from linear logic. PWD just indicates how often if you're generating a sentence, PWD tells you how often you should make the choice for that particular word connector sequence pair. And so, but you can only pick one, right? Shades of wave function collapse, right? OMG, how did that sneak in there? The hat E is, by the way, it's a unit basis vector. If you're familiar with vectors, that's all that the hat indicates. It's the unit length vector. Okay, so now I have a bunch of these. Now what? All right. I'm going to generalize. I need to generalize from the specific to the general. I'm going to skip a slide. I have my slides slightly in the wrong order. When I say I threw the ball, I want to generalize from throwing the ball to this saying throwing some common noun, any throwable object. And then I want to generalize, well, I'm going to take some action verbs, something I can actually throw or move and apply that to some throwable, movable object. That's the generalization. I have a verb connecting to an object, that object is going to be a common noun. There's a determiner there. So that's the generalization I want to make. Okay. How do I do that generalization? Well, I want to do it by means of similarity. Similarity, well, I mean, there's a choice of similarities you can use. There's Jacquard distance is popular. Dot product, the cosine distance is very popular, certainly in the neural net crowd. There's a problem with the cosine distance. It turns out it's not very good, and there's a reason for this. Probability space is not Euclidean. Probability space is a simplex. Right? cosine products are great for Euclidean space, right? Cosines are Casimir invariants for Euclidean space. But here I actually have a the shape of a simplex. Taking orthogonal complements is a bit of a problem. And so now I get back to the definition of mutual information again. This time it's a symmetric mutual information. It's again between two words, but instead of saying I have a word on the left, a word on the right, I'm now taking a dot product of the word vectors. Right? The asterisk here is the same wildcard asterisk as before, right? It's a summation of over all possible other words that may occur in that location. There's actually a fancy way of looking at the mutual information. You can, there's an associated Feynman diagram for this thing. The wildcards are actually the contribution from the vacuum. It's a rather strange beast. Okay, but a brief diversion, okay? I graphed a number of word pair similarities here, about 2/3 of a million different words, and you see a parabola in the diagram below. This is on a log scale though, so parabolas are in fact just bell curves, Gaussians, right? Normal distributions. And my question is, at this point, why is this a bell curve? All right, I took some word pairs from English, pumped them through a grammar detector, formed these mutual information, formed these maximum spanning tree parses. Why would these come up as a bell curve, right? As far as I know, there's no theory for this. Nobody's looked at this. So by this point, I've talked about very simple, basic recurring themes that you see in machine learning, and yet something as easy as the statistics seems to be unknown and unexplored. There's no known theoretical background for this. Now, today's pet theory for this is, my pet theory is that it's a GUE, but I certainly cannot prove that mathematically. So anyway, at this point, we are learning how to generalize. We've learned how to generalize. The biggest problem with mutual information or using mutual information as similarity is that very rare words often have a very large mutual information. It's a poor strategy, I think, to start assigning, to start merging together, to start clustering very rare words into grammatical classes. You really want to sort of start with common words. The proposal I make here is to take the average probability, right, of two words. You take that average, take the log, add that to the mutual information. You'll get an expression that automatically weights common words much higher than uncommon ones. When in a log, once you take that logarithm, that 1/2 of averaging turns into a square root. So you have this very funny looking equation that I've drawn here involving a square root. You won't find this in textbooks anywhere, but it's completely natural. Okay, so generalization. Oh dear, I have to correct this. That matrix that I created of word disjunct pairs can be factored into a left, central, and right block matrices. The equation I've written here is that factorization. The letter G, I'm using the letter G to stand for the word class, G prime here for a grammatical or a syntactic relation. Right, so there are many words that behave similarly. So that's my left factor. There are many syntactic relations that are shared between many sentence constructions. That's the right factor. In the middle, I have a dense, highly connected matrix. The central part, it's not at all sparse. The left and right matrices are really quite sparse. The central one is not. The central one encodes the grammar of the language. This is, in fact, okay, I've expressed clustering here as a matrix factorization. This is, in fact, the de facto organization of the existing link grammar dictionaries. Right? The people who wrote the dictionaries were not thinking of matrix factorization, but de facto, that's what they have done. They've done it tediously. They've done it by hand. The link grammar, English and Russian dictionaries are hand created, but that's what they did. So the point here is, although I'm talking very abstractly, this is in fact what linguists actually do when they practice linguistics in their spare time in their office to create their papers. They are in fact, when they specify syntax, they are factorizing this kind of a matrix. Okay. Now, this is, there's sort of a key insight into all of this. Neural nets also accurately capture that dense interconnected central region. That's why they work. Right? Neural nets necessarily perform dimensional reduction on the sparse and left and right factors. By erasing those left and right factors, neural nets no longer become interpretable. Right? That's the magic that gets hidden in neural net weights. That's the magic that people can't disentangle. That's why they are not interpretable. They don't know what to do with the weights. The goal of the algorithm that I've described here is to do what these neural nets do, but to do it in a way that is interpretable and understandable by human beings, right? You can look at it and you can say, oh, here are the factors. Here are the words that belong to this class. Here's the words that belong to that class. Boom, right? I'm done, right? In a sense, I'm almost done with this presentation. Well, okay, not quite. There's a bit more to go, but I want to sort of pause here and recapitulate what we've done so far. Right? So here's the learning algorithm that I sketched in the last few slides. Right? There's a pairwise correlation in a corpus. Right? Go through the corpus, count the number of pairs that you see. Compute the mutual information between those word pairs. Use them, construct a maximum spanning tree, bust that up into jigsaw pieces, and now gather those pieces up into piles of similar pieces. Look at how those specific word disjunct pairs are similar to one another. Those piles of jigsaw pieces, those are your clusters, right? That's your matrix factorization. You assign them by similarity. Right. The result of this is a grammar that describes that particular corpus for that particular language. And this is just an ordinary conventional linguistics grammar. This is what linguistics theory, the kind of grammars that they generate. This is not something weird and unusual. This is actually really quite conventional. Let me resume now. There's a set of trivialities that I sort of want to go through to reach the final conclusion. Let me remind you again, jigsaw pieces are compositional and they're freeform hierarchical. Right on the right-hand side of this diagram, I've drawn a two-word puzzle piece figure, a hot potato, right? It behaves as if it was one word. There's still a connector needed for a determiner. There's still a connector needed for some sort of a verb that will be there when you put it in a sentence. So if, a partially assembled jigsaw puzzle is just like an individual piece. You still have unconnected connectors going off in all directions. On the right-hand side, I have a sketch of anaphora resolution. Right? You've developed a grammar for individual sentences, but what about connections between the sentences? The example here says, if you can't read it, it says, Susan held her hat, she loved it. Well, she is Susan, it is the hat, her hat is Susan again. These are all connectors, they're running between the sentences, they're running between the references, right? So jigsaw puzzle pieces allow you to do this recursively. I've put together sentences, but now I have to move up into paragraphs, into entire texts. I'm just saying repeat this process, right? This is hardly a new idea. People have talked about this for many decades. I'm hoping that what is different here is that I've presented you with an algorithm, a theoretical framework for which software can be written in which these ideas can actually be applied and carried out. Move on. Okay. Now, in a certain sense, we've gotten lucky with language. Language, I already had words. If I'm working with audio or with video, I'm not so lucky. Audio and video is very dense. Video has lots of pixels in it. Audio has audio samples. How do you deal with those? We need some sort of processors to convert sensory. I have to be careful. That converts sensory input into something that resembles words so that I can apply this algorithm to it. The proposal here is to generate random processing pipelines and try them out. On the left is on the left of this diagram, I've drawn a random audio pipeline, a low-pass filter, and a chirp filter. On the right-hand side, I've drawn another sort of random sequence of filters. When I run audio through them, do they correlate? Do they have a high mutual information between them? If they do, I say, great, there's actual important information encoded here. If not, throw them out and try again. Right? These will eventually hill climb their way to meaningful filter sequences. This is very much a classical optimization problem here. The only difference is the objective function is it's the old-fashioned maximum entropy principle. This seems like an old idea. It's a naive idea even. It feels like there's nothing particularly new, but you can couple this to the grammar learning algorithm and walk up the hierarchy of abstraction from raw sensory inputs up to a grammar of what is there. This is the part that I think nobody's done before. This is the hope. Now, key point here, everything here is symbolic, everything is interpretable. I can show these filters to any good engineer. He can look at those filters and I say, oh, I know exactly what that filter is. OMG, it's even labeled. It's a low pass filter. It's a chirp filter. It's obvious what that is. That solves the symbol grounding problem, right? When I use the word, I hear whistling in the distance. When I use the word whistle in a sentence, I know what that corresponds to now. It corresponds to a particular filter sequence. You can see what that is. You can interpret that meaning. They go together, right? I know whistle when I hear it. How do I explain it? Well, the grammar explained what it was. The frame problem is a problem that asks, what parts of the environment are important for making decisions? The answer here is the parts of the environment that have been filtered out by the current active filters. Well, what are those? Well, those were the ones that were learned by applying mutual information to extract the similarity, to factorize, to generalize the common situations that we find ourselves in. Right? This naturally leads to common sense reasoning. Now, reasoning, okay. Old school AI work on reasoning harks back to the foundations of mathematical logic developed in the first half of the 20th century. Right? The trope is that common sense is somehow like mathematical logic, right? There's a rational actor of the Enlightenment, of economics, and that's not it, of course, right? That's not what common sense is. So I have a joke here that I've diagrammed on this page, right? Doctor, doctor, it hurts when I do this. Well, don't do that. Right? You know, they say never explain a joke, but I have to explain this because it's important. So, okay, the joke is funny precisely because the logic is correct, but it fails in the meta problem of what doctors do, of why, you know, why we went to that doctor in the first place. All right. The common sense reasoning context is that there are certain expectations of what takes place in a doctor's office. That's the frame. That's the frame of the frame problem. Doctors do a number of things, and one of these things that they do is they cure ailments. Frames of the frame problem are they're like lexical functions of linguistics, of MTT, you know, meaning text theory, right? If you can learn lexical functions, you can learn the frame in which common sense reasoning applies, right? The network of things that happen in a doctor's office, you've learned that network, you navigate it through lexical functions. It's the same way that it's the same thing, right? The reason the joke is funny is when that logical advice of don't do that, it fails to match up with the rational expectations of what should have happened in the doctor's office. Well, what are those rational expectations? Well, those are the things that correlated with doctor's visits, right? I saw them with high mutual information, right? So this is the joke. This is the joke that's explained, right? You can, so my outrageous claim here is that this can be done. Reasoning can be found, can be discovered in this kind of a way. It's not God-given. It's not hard-coded by some programmer. It can be learned algorithmically. Here's how it can be done. That brings me to the end of my talk. I've skipped over some conclusions. I skipped over talking about experimental results. There are actually a lot of them. I've been working on this project for a while. The experimental results are, well, they're rather, you know, they're curious. It's like that Gaussian distribution that I showed earlier. It's where did it come from? Where did it, you know, search engines don't seem to know the answer to this thing, right? So there's a lot left to do. I mean, what I've talked about seems simple and obvious. There's little or nothing published on this kind of thinking. There's little software that is usable. There's what software there is not very well engineered or scalable. So despite the simplicity of the presentation here, this is essentially, it's unexplored territory, right? It looks really great from what I've, you know, from the exploration so far, but this is very much an opportunity for any student who wants to make their mark on the AGI world. Yeah. That's the conclusion of my talk, and I'll say thank you. Are there questions?